Let us look at the simple harmonic motion from an algebra-based point of view. We are not going to use any calculus in deriving the expressions. We have a horizontal spring that it is originally not deformed. This is the natural length of the spring, and if we are choosing a horizontal motion, the result would be the same with a vertical motion. We have to choose an x-axis. We attach an object to the spring and stretch it. We stretch it up to a position A. At this moment, the forces acting on the object are the force that I applied, the elastic force developed in the spring due to its deformation, the weight of the block, and the normal force. This is the free body diagram of the block at this position. We are not going to worry about the weight and the normal force. We are going to look only at the horizontal motion. So at this point, because the object is in equilibrium, the force of pull and the elastic force are equal to each other. If I let the object go, the force of pull will disappear, so the free body diagram will become simply a story of three forces. Again, the normal force and the weight, we are not going to include them in our discussion. So there's only one force acting on the object, and that is the elastic force. Because of this elastic force, the object will start moving. And the object will oscillate between position A and position minus A with respect to 0. And this symbol A comes from the word amplitude, because we are going to say that this is the amplitude of the motion. The quantities that are known in this problem are the mass of the object and the spring constant of the spring. And we are trying to find 4 quantities. We are trying to find the position of the object at any given time. We want to find the velocity of the object at any given time. We want to find the acceleration of the object at any given time, and we want to find the period of the motion. These are the 4 quantities that we want to calculate for this motion. Now I know for sure that the object will always be between A and negative A. It's going back and forth between these 2 extreme points. But if I'm starting the stopwatch here, when the object is here, it's equal to 0, and x is equal to A. So if I'm starting the stopwatch when the object is at A, I would like to know later, at some other time, what is this position. Where exactly will the object be? I'm trying to predict that. So for that I need an equation that expresses x as a function of time. So at any given position, let's draw this again. So we said that this is 0, this is A. The object at some point, let's say it's here at position x. Right? At this point, the only force acting on the object is the elastic force. Now we remember from Hooke's law that there is a negative sign here because the force opposes the deformation. If the spring is stretched to the right, the elastic force will be to the left. If the spring is compressed to the left, the elastic force is to the right. That is a force that develops in the spring and opposes the deformation. So we need this negative sign. So because here we are on the right side of the zero, right, the elastic force will be pointing always to the left. And this force will lead to an increase in speed if the object is moving left to right, or to a decrease in speed if the object is moving right to left. So in the first case, if the object is moving to the left, this elastic force, we can call it a pull. But if the object is going to the right, the elastic force will be a resistance or a friction. Regardless, this is the expression of the elastic force. And we know Newton's second law that says that the net force acting on an object is equal to the mass times acceleration. So in this case, this will become negative kx is equal to ma. We solved numerous problems using Newton's second law in physics 1, but we cannot do that here. We cannot use the same approach because the force kx is variable. It depends on where I am, where the object is, right? If the object is at 0, the elastic force is going to be 0. If I'm here, the elastic force is going to be Ka. If I'm somewhere here, we chose a random position between 0 and A, the elastic force is Kx. So because this force is variable, I cannot simply say that A is negative Kx over M. It doesn't work like this. And the reason is the acceleration itself depends on the position. So because of that, we have to use calculus, and this is the part that we are going to skip. However, we are going to look at the expression, the result from calculus, and we'll see that that result is correct. So the result that comes from calculus is that the position of x as a function of time is a cosine of omega t, in which omega is 2 pi over the period of the motion. This is the result that we have to accept that is produced using elements of calculus. Amplitude times cosine of omega, which is given by this, 2 pi over the period, times the time. We can see that the units are indeed all right, because cosine of omega t does not have any units. 2 pi over period has inverse second, units 1 over second multiplied by time, so it has the units, no units, which is okay. And the amplitude, whatever units it has, centimeters, meters, millimeters, will carry over to x. And another thing that so the units of x are, let's say, the meter, and that is okay, because this is the unit of the amplitude at the end of the day. And the other thing that we see easily is that the value of x is always less than 1. Sorry, it's always less than the amplitude, and that is also acceptable. Less than the amplitude and greater than the negative a. That is consistent with the fact that the cosine function, of course, goes between 1 and negative 1. So when we multiply this by a, it translates into this. And this is consistent with what's happening, because remember, the object oscillates between position a and minus a. So this is the first test that this equation is accurate. It reflects the experiment. And we can continue by testing this expression to see if at certain values, again, it reproduces what we expect. So at t equal to 0, indeed, x of 0 is a cosine of 0. Cosine of 0 is equal to 1, so it's equal to a. And this is what we expected, because remember, the object was here at time equal to 0. Now, at some later time, the object will always be somewhere else, but there will be a time of particular interest to us, and that will be a quarter of a period. Why am I choosing a quarter of a period? What is the period? The period is the time it takes the object to go back and forth once. So a quarter of the period is the time it takes the object to go from here to here. The second quarter is from here to here. The third quarter is from here to here. And the fourth quarter is to come back. So again, the period is the time it takes an object to go back and forth once. And because there is no friction or anything, this time will be split into 4 equal parts. One part to make this motion, to travel this distance. The second part is to go here. The third part is to come back, and the fourth part is to complete the motion. So at t equal to a quarter of a period, I expect x to be 0 based on this picture. And let's see if that is the case. It becomes a cosine omega times t over 4, or a cosine 2 pi over t times t over 4. And this becomes a cosine pi over 2, which is indeed 0. So the equation works. We can go back and test for other positions, but it is clear that the equation works. So we found the position as a function of time, and the position as a function of time is going to be a cosine omega t, in which omega is given by 2 pi over the period, and we saw that this expression works. Now, if I want to find v as a function of time, in principle, I would have to take the derivative of the position. I would have to do the derivative of this, but of course this requires calculus. If we want to avoid calculus, we can calculate the average speed between two time intervals that are very, very close to each other. So I'm going to calculate the average speed between when the object is at the position t plus delta t minus the position of the object when it is at a time t. The position of the object is time t. And of course this must be divided by the time. So it is very hard to draw this because I want this delta t to be very small. But the idea is, if I want to find the velocity of the object at this point, I'm going to calculate the position at this point. Then I'm going to calculate the position at a later time, take the difference between these two positions and divide by time. So this is what I wrote here. If I want to find the velocity of the object at time t, I'm going to calculate the average velocity of the object between time t and time t plus delta t. This is the basic definition of average velocity. So let's continue here. So x at time t plus delta t will be a cosine of omega t plus delta t minus a cosine of omega t and divided by delta t. I just replaced the x by its expression. And this becomes a cosine of omega t plus omega delta t minus a cosine of omega t divided by delta t. And we can use a trig identity that says that cosine of a plus b is equal to cosine a cosine b minus sine a sine b. It is one of the better known trig identities. So let's see how this works. Of course, we apply this for the first term. So I'm not worried about it. Cosine a plus b will be cosine ab, which if I apply it here, it will be a cosine omega t plus, a cosine omega t cosine omega delta t, it is the first term, minus a sine omega t sine omega delta t, and the original a cosine omega t is not going anywhere. It looks like it's getting out of hand. Perhaps you wish now we just used calculus. However, in order for this velocity, the average velocity, to be the velocity at this time, in other words, if I want this average velocity to become instantaneous velocity, I want delta t to be very small. So if I want the average to be able to call it instantaneous, then delta t must be very small, and by very small I'm saying it must go towards 0. Or I'm going to say very, very small. So when that happens, let's see. When that happens, this term here is very small. Very small means it's very close to 0. Cosine of 0 is approximately 1. So when omega delta t is very, very small, this whole term here will be equal to 1. So pause for a moment to appreciate this. I can do this only if delta t is very, very small. And it is, because I'm not interested in the average velocity between two different points of the oscillator. I'm interested into the average velocity between 2 points that are very, very, very close to each other. So, of course, it will take a very, very, very little amount of time for the object to travel between those 2 points. The purpose of this discussion is not to find the average velocity between this point and this point. No. The purpose is to find the velocity at this point, and this we break it into two tiny, in between 2 points that are very, very close to each other. And consequently, the time it takes the object to go between those 2 points, to travel between those 2 points, is going to be very small. So because of that, this becomes 0, and 0 is equal, cosine of 0 is equal to 1. So now we can see that this term and this term cancel. So right now we are left with minus a sine omega t sine omega delta t. We are not done, of course. We'd like to make it look a little nicer. And this is the time to introduce an approximation that we will use a lot in physics, including in Physics 2 course. And that approximation is that for a very small angle, so for an angle theta that is small, the sine of the angle is approximately equal to the tangent of the angle, and approximately equal to the angle in radians. So everything has to happen in radians. Feel free to test this using a calculator. So this is called the small angle approximation, and it has applications well beyond this topic. So if I have a very small angle, maybe I should say a small angle, I shouldn't call it very small. And if you are wondering what qualifies as small, use a calculator and test it. I would say an angle less than 15 degrees is acceptable. So feel free to convert 15 degrees to radians, and then you will see that sine of theta is approximately equal to tangent of theta and approximately equal to theta in radians, up to about 15, even 20 degrees. So if we go back here, clearly omega delta t is very small, because remember that delta t is very small. So sine of omega delta t, right, is small. So if it is small, I can use the small angle approximation. So I'm going to say sine of omega delta t. I can approximate it by omega delta t. According to this, of course, it's also approximately equal to tangent of omega delta t, but I don't need tangent in this discussion. So now if we go back all the way here, my average velocity from here, right, has become negative a sine of omega t. The sine omega delta t, as we just saw, becomes omega delta t. And let's not forget that we have to divide by delta t. Delta t cancels out, and from here I get that average velocity is negative a omega sine of omega t. This is something that if we use calculus, we have found a little earlier, a little sooner, but this is how it works. So and now of course I can drop the average sign from here, right? I'm going to say this is actually the velocity of the particle at the object, whatever it is, at time t. So actually this is perhaps the expression that I should have boxed. It's exactly the same as the previous one, except we drop the average, because when the time is very, very small, again, when the time is very, very small, the average velocity, right, becomes the instantaneous velocity. We can do something similar to find acceleration. So if I want to find acceleration at time t, I will find acceleration, the average acceleration over time delta t. So it will be the velocity of the particle at time t plus delta t minus the velocity at time t and divide by delta t. And if we follow the same procedure, and we make delta t equal, make delta t very small, we will find that the acceleration, the average acceleration, which of course becomes the instantaneous acceleration at time t, will be negative omega squared a cosine of omega t. But this is an exercise that I think everyone should try on their own. The identity that we need here, it is, we're working with sine, right? So you will need at some point that sine a plus b is sine a cos b plus sine b cos a. This is the equivalent of what we used earlier when we needed cos a plus b. So I think this is a good exercise for everyone to try at home. And finally, we would like to find the period. Remember the period which is 4 times this time. So if we want to find the period, it comes directly from here, right? From the definition of the omega. So t is 2 pi over omega. But when it comes to when we solve this differential equation, which led to this result and which we skipped, in that case, omega, the relationship between k, m, and omega is given by this. So k is equal to m omega squared. So these two expressions are what we kind of need to accept without using calculus. So to summarize the simple harmonic motion, the equations are x of t is equal to a cosine omega t. We saw where it is coming from, but we had to accept the result just because we wanted to use only elements of algebra. The velocity at the time t is negative omega a sine omega t, and we derived it using exclusively algebra elements. And in the process of doing that, we learned something new, the small angle approximation. Similarly, the acceleration turns out to be this, and this is a good exercise for everybody. And in all these expressions, omega is 2 pi over the period. Omega is 2 pi over the period. And finally, the relationship between the period, the mass, and the spring constant, right? It is 2 pi square root of m over k. It is the expression that comes when we put everything together. And of course, one last tiny step. Once we have these expressions, we can find the energy. As the object is moving, it will have two types of energy. It will have kinetic and it will have a potential, elastic, if the motion is horizontal. If the motion is vertical, we have to add gravitational potential energy. But for now, let's focus on this. So the kinetic energy is 1/2 mv squared. The potential energy is 1/2 kx squared. These are things that we learned in Physics 1. So from here, the kinetic energy, maybe I should use Ke to avoid confusion with the spring constant. So the kinetic energy is 1/2 m. And V we found already, minus omega A sine omega t squared. So this becomes 1/2 m omega squared A squared sine squared of omega t. This would be the kinetic energy at time t. The potential energy is 1/2 k x squared, a being a cosine of omega t. Okay, so this clearly becomes 1/2 k a squared cosine squared of omega t. This is the potential energy at time t. If I want to add them up, so the total energy, I add them up and I take into account the fact that k is equal to m omega squared. So when I do that, I will replace here k by m omega squared. So this whole thing becomes 1/2 m omega squared a squared, which I can factor out. These terms are identical. And I'm left with sine squared omega t plus cosine squared omega t. And this is equal to 1, is the famous trig identity. Sine squared plus cosine squared is equal to 1. So this leads to 1/2 m omega squared a squared. And again, if I take into account the fact that the two are equal, I can rewrite it as 1/2 k a squared. So to summarize, I can say that the total energy is at any given time is 1/2 mv squared plus 1/2 kx squared, but at the same time this is equal to 1/2 ka squared. This happens when the object is at x equal to plus or minus a, and this is also equal to 1/2 the maximum kinetic speed, which happens only when the object is at x equal to 0. So I have this identity, which looks maybe a little weird in the sense that it has more than one equal sign in it, but the advantage of it is that I can pick and choose whatever I want. If I am, depending on the problem, I can work with this term and this term, or with this term and this term, or with these two terms. But please take a moment to appreciate the fact that when the object is at the extreme positions, there is no kinetic energy because the object is clearly not moving, it stops for a moment. And when the object is at the equilibrium position, there is no potential energy because the spring is not deformed.